This is a hypothesis test of the mean, and I will give you a minute to read through the example here. Once you've read through the example, first let's talk about our null hypothesis and our alternative hypothesis. Okay, so these students are taking a college entrance exam, and our null hypothesis is going to be the status quo about the mean. And they tell us that the mean score is 24. Okay, that's our status quo. We just assume that that's what it is. But we think that our students are scoring above 24. So our alternative hypothesis is going to be that mu, our population mean, is greater than 24. All right, so a few things to note about this. Let's look at our other numbers here. I see the number 200. Okay, we're taking a sample. That's our sample size, so n equals 200. I see that in our sample, we have a mean math score of 24.6. So that is our sample mean, which is x bar. That is 24.6. And the standard deviation of that sample is, they tell us, is 3.5. Okay, so that's the letter S. That's our sample standard deviation. And we're going to look for a few things. Okay, our requirements to do a t-distribution. So first, they don't tell us anything about outliers or a box plot. So if we don't know anything about outliers, we have to make sure that our sample size is greater than or equal to 30, and at 200 that is correct. They don't tell us anything about this being normal. So we don't know anything about that. Now we do know that our sample is random, so that's good. And we also are going to assume independence because our sample size is less than 5% of the population. Okay, we can assume that there will be 100,000 or more college students taking the entrance exam, and our measly 200 is certainly going to be less than 5% of that. All right, so let's go and let's find our test statistic. Okay, we are going to be given an alpha of 0.05. That's our level of significance. And our test statistic here is a t statistic. And so we have an equation for that. And it's going to be x bar, our sample mean, minus our population mean, mu, is going to be on top of our sample standard deviation over the square root of sample size. Okay, and we have all these numbers now, so we can just go ahead and plug them in. We have our x bar is 24.6, and subtracting the mu is 24, and it's all over our S. Our sample standard deviation is 3.5 divided by the square root of sample size, which is 200. And we put that into the calculator, and it's going to tell us that that is 2.424366, and on and on and on. They want us to round it to 2 decimal places. So 2.42, that's going to be our T-naught. All right, next we're going to find the p-value. Okay, we're going to approximate the p-value. So let me make a little space here. All right, I'm not able to make any space, but that's fine. P-value All right, we know that this is, since it is greater than, we're going to be looking at the area to the right. And so that's good because the table we're going to look at is already going to be set up for that. And our degrees of freedom, if our n is 200, we're going to be looking for degrees of freedom of 199 or the next number below that. So let's take a look at what's on the table. We don't have degrees of freedom of 200, so we're going to go to our next closest one, our 100, and we are looking at these values here. Our test statistic was T0 was 2.42, and when we look somewhere between these two, okay, somewhere between, so our p-value is going to be between 0.01 and 0.005. All right, we're going to compare that to the alpha, which our alpha is 0.05. It's over here. Okay, so our p-value, which is less than 0.01, is smaller than our alpha. Okay, and what happens when we get that? When your p-value is less than your alpha, we are going to reject the null hypothesis. Okay, status quo, we can no longer say that that's okay. This p-value is so small, okay, such a rare event with our sample, that we are going to reject the null hypothesis. Okay, there is sufficient evidence to conclude that the population mean is greater than 24. All right, so reject null hypothesis. That's it.